So Peter, I cannot use chat, but I will send you by email. Is it okay?
Or of course, yeah. Send it by email and then I'll post it. Okay, so while people are joining in, I want to make a couple of remarks. So welcome everybody. This is the workshop on elliptic integrable systems. So couple of points here. So we have 9 speakers agreed to talk. Thank you guys very much for the agreeing to talk in such notice. So we'll have 2 evening sessions, 2 morning sessions. So it's sort of an attempt to make a global workshop, right? As you understand, it's impossible to have daylight at the same time in Japan, US, and Europe. So we'll have this evening and morning session. So today we have 2 talks by Andrey and by Junichi. Each talk will last for 50 minutes, and that includes questions. And the format is very pretty much feel free to ask questions at any time. No need to wait till the end. So we try to make it as informal as possible. So those of you who are familiar with our Berkeley math physics seminar, it will be close to that one. So yeah, we will record all the talks, which actually means that your questions will also be recorded. So and then we'll upload them on YouTube shortly after. So if you have, so Andrey just sent me his notes, the PDF file. I also ask all speakers to do the same. So email them to me, and then I'll upload the notes to the workshop website. So slides or notes, whichever you prefer. So all the materials will be available. And then so the workshop is called Elliptic Integrable Systems, but it will, most of the talks will be about those, but in general, it's about various topics in mathematical physics, but with strong emphasis on elliptic models. So in particular, this double elliptic model here, the DEL, we had some recent progress in understanding of its quantum structure, eigenvalues and eigenfunctions, and we'll hear, I think, 3 or 4 talks about this system itself. So right now we'll hear a talk from Andrey about enumerative algebraic geometry, some equivariant elliptic homology of Hilbert schemes of points and other stuff. And also there'll be some geometric representation theory talks later. Yeah, any questions about logistics or anything? So while there's like 1 minute left, we can all look at this table. So for those of you who don't know what this is, so this is a classification of integrable many-body systems based on periodicity properties of its momenta and coordinates. It's Hamiltonians on momenta and coordinates. So we have rational, trigonometric rational, and so on. So the elliptic models, they lie here. So one of them is elliptic Rosiner-Schneider, and the celebrated Dell model will be in the corner. So in a sense, all many-body systems, they are some limiting cases of the Dell system. And we'll hear a lot about this model later, but not today, but tomorrow for sure. Okay, so it's 5:10. So then without further ado, I quit sharing screen, and then so Andrey can, so we'll first hear from Andrey about his talk is called Elliptic Stable Envelope for Hilbert Scheme of Points on C2.
Right. Thank you, Peter.
Yeah, I think you can share now. Yeah.
So I can start sharing screens, right?
Yes.
All right. So let's see. Is it visible?
Yeah, we see all your calculations. Yes.
All right. So now I'll try to go full mode. Right. Is that better?
Yes.
Okay, good. So yeah, thank you, Peter. And as a person who is giving the opening talk, I would like to thank Peter for organizing this workshop and for creating this nice opportunity to share our knowledge and understanding of elliptic integrable systems. Yeah, and today I'd like to speak about elliptic stable envelope for Hilbert schemes. So I'd like to start with some small reminder about the Hilbert scheme. What is this? So do you guys see my pointer on the screen?
We do. Yeah.
Good. All right. So Hilbert scheme of points of n points in C2 is defined as the following set. So it's a set of ideals J in a ring of polynomials in two variables x and y, so that the codimension of ideal is equal to n. So it is known that this is actually a nice smooth variety of dimension to n with a bunch of interesting properties. The important for us would be the action of a torus on this variety. So there exists an action of torus T on X. Torus T is a two-dimensional torus, which basically acts by scaling variables X and Y by T1 and T2. Right, so that induces some obvious action on here. And throughout my talk, from time to time, I will use variables T1 and T2, so-called equivalent parameters. And sometimes it will be more convenient to use variables A and H bar, and those are related to T1 and T2 by these algebraic relations. So H bar is just a product, and A is a ratio of T1 and T2. So important thing is the set of torus fixed points. So this torus acts so that only finitely many points on X are fixed, and those points are labeled by Young diagrams with n boxes. So it's actually pretty easy to see. It, for example, if you look at the ideal J generated by these three monomials, it is actually represented in this picture. So you can think about polynomial ring as a vector space over C, just an infinite dimensional vector space spanned by monomials in X and Y. And then if you look at the ideal generated by these three monomials, well, this is everything that is shaded in this picture. Okay, so shaded region is exactly the ideal generated by these three things. And the rest of the boxes form Young diagram, And the number of boxes is exactly the codimension of this ideal. So in this case, the number of boxes is equal to 7. So this monomial ideal is a fixed point on Hilbert scheme of 7 points in C2. All right. And so this variety has a lot of nice realizations. For instance, it can be understood as a Nakajima queer variety associated with that queer. So if you don't know what's queer variety, it's fine. So we don't really need it in this talk. But just to say that from this picture, it's, for instance, obvious that this variety is actually a symplectic variety. And guys, you know, I'd like it to be like super informal talk. And if at any point you have any questions, just, you know, don't worry and stop me whatever question you have. All right, so this is a Hilbert scheme. And then why it's interesting to study Hilbert scheme and representation theory. So there is a general construction of quantum groups which act in equivariant K-series of Nakajima queer varieties. So for instance, there is an action of a quantum group, which is sometimes called quantum toroidal GL1 with parameters T1 and T2 on equivariant K-theory of Hilbert scheme of n points. Sorry, not n points, but you just take a sum over all possible n's. So it's an infinite dimensional representation, which is as a representation isomorphic to so-called bosonic Fock space. So as a vector space, this is just a space of symmetric polynomials. So, you know, something like this. It's a space of polynomials on infinitely many variables, right? Which is in physics, we sometimes call them bosons. And there is a pretty interesting algebra acting on this space. So this algebra can be described very explicitly by generators and relations. So generators of this algebra, you know, generators of this algebra correspond to points on two-dimensional integral lattice. So for each point in this picture, there is some generator of this algebra, and then those generators subject to some commutation relations. Those are pretty complicated, so I decided not to write them down because we will not need them. But interestingly, there are some interesting subalgebras in this algebra. So for instance, if you take any line which goes through zero with some rational slope, for instance, this red line here in this picture represents a line with the slope 1/2. Then elements of this algebra, generators of this algebra sitting on this line, form Heisenberg subalgebra. For instance, it means that the commutational relations among them are pretty simple, right? So they'll compute as in this formula. And you know, some of those Heisenberg algebras are pretty familiar objects. For example, so-called slope zero Heisenberg algebra. So it's just this set of generators sitting on this horizontal line, right? So denoted by blue. They also form a Heisenberg algebra with well-known action on the Fock space. So for positive n, those generators act as as derivative in n. For negative n, it acts as multiplication by, probably here it's going to be minus n sign. So that, right, so there is some mistake here. So it's p minus n because n is negative. That doesn't really matter. So this action is pretty familiar on a Fock space. There is another sort of important Heisenberg algebra, which is actually commutative. So it's called vertical subalgebra. It corresponds to generators sitting on that vertical line here. And those Heisenberg algebra sort of degenerate. They actually commute with each other. And so in particular, they can be diagonalized simultaneously diagonalized on a Fock space. And those generators, they act exactly as so-called McDonald operators on a Fock space. In particular, they are diagonal in McDonald operators. All right. So yeah, but for general Heisenberg subalgebra with general slope, well, the action is more complicated, and for general non-vertical slopes, those Heisenberg subalgebras are non-commutative.
Sorry, a question?
Yep, sure. Hi, Gleb.
Yeah, hi. Just make sure, since I don't know very much, but like dim algebras, they also have the same picture, or like what is the difference?
Well, yeah,
like,
so
the same type, or just
yeah. So the short answer is that this is exactly the dim algebra. So
is it by definition, or is just like some observation you need to make?
No, it's just by definition. So I didn't list all.
Yes, I think there are 4 or 5 different names for the same algebra. So these are 2. So there's that, and then there's also something like Greenfield double of shuffle algebra, and 2 more, I think.
There's also this algebra is sometimes called like elliptic hole algebra, quantum toroidal. I just think that quantum toroidal is the most economic name, and this structure describes the name best.
Okay,
Yeah, but
thank you.
Exactly, yeah, but that's exactly Dean Giohara algebra, Mickey algebra. All right, let's move next. So for this slide, we only need that I have a Fock space and I have an action on the Fock space of this algebra, and it is known that the Fock space has many interesting bases, and for each slope, for each given slope, there is a special basis in a Fock space in which these slope Heisenberg subalgebras, as in this picture, act sort of in the simplest possible way, in a sense, or maybe like the most beautiful way. For instance, if you take basis of a Fock space corresponding to the Heisenberg zero algebra, zero slope Heisenberg algebra, that is, very well known Schur polynomials. And this action, multiplication by n, if you multiply Schur polynomials by n's power sum and expand it in Schur polynomials, then the action is described. So the coefficients of this expansion are described by so-called Pierre rules. So basically, Pierre rules describe how zero slope algebra acts on a corresponding basis. Well, it's easy to guess what's going to correspond to infinite slope subalgebra. As I mentioned, infinite slope subalgebra acts in a diagonal way in McDonald polynomials. And so McDonald polynomials is a natural basis corresponding to so-called infinite slope. And then we have a bunch of less known to people polynomials labeled by rational number, so labeled by slope. Sometimes these symmetric polynomials called rational Schur functions. And the action of a Heisenberg subalgebra with slope A over B in this basis, well, it is known. It's you can look at the paper by Andrey Smirnov, which is called AB Pierre rules. So it's a generalization of Pierre rules from slope zero. All right, so we have like a bunch of a lot of different bases in a Fock space, and those bases, you can think about them as bases which sort of interpolate between Schur functions and McDonald polynomials. All right, so yeah. Okay. So these polynomials, those bases were studied. Actually, not that many people studied these polynomials, but one of those few works is so-called paper called the infinitesimal change of basis of stable basis. It's a paper by Zhenya Gorsky and Andrey Smirnov. And what they studied a transition matrix between basis of two two sure polynomials, which which are described as follows. You have some rational number. You consider what is the basis right after that rational number and right before. And so if this epsilon is a very, very small positive number, this matrix, the transition matrix between these two bases, actually well defined. And they call it they call this this matrix like the matrix of infinitesimal change of stable basis.
So epsilon also must be rational, obviously, right?
Epsilon may epsilon must be rational, but it does not really matter. You can also think about it as a real parameter, but very small. Like more precisely,
you only define the subalgebra S only for rational AB, right?
So S is not subalgebra. S is a basis in Fock space.
Right,
right?
the basis, but it's defined by the slope, right? And slope is only rational.
Yeah. Yeah, and basically you study how this basis changing across the wall located at the A or B. Okay. And well, this is some matrix labeled by two partitions. It's a transition matrix. And for instance, this how this matrix looks look in a simple example. If you take a Hilbert scheme of 3 points, then I have 3 partitions corresponding to these Young diagrams. Then you can take some rational number, say the number 1/2, and ask like, what is the how is the basis of rational short polynomials change from before to right after this number? And well, in general, those matrices look like this. It's almost diagonal matrix, so it has ones on diagonals, zeros almost everywhere except some positions, right? And then some rare positions you'll see some polynomials in A and H bar. So those are my current parameters. And what is they made a couple of very interesting observations about those matrices. For instance, they discovered that dependence on the equivalent parameter A, I recall A was like a ratio of T1 and T2. And so dependence on A is actually very simple. So they found that there is basically a monomial matrix, diagonal matrix with monomials in variable A on diagonal, so that after the conjugation by this matrix, dependence on A just disappear, right? So which basically means that dependence on A is always like true monomial, like here, right? So it's a polynomial in H bar, but it's always monomial in A. And after some simple conjugation, dependence on A just disappear. And what is more interesting is that, when you factor out A, we just forgot about A, and now we look at these matrices which depends on H bar. They found that those matrices not actually depend on a rational number, like 1/2 here, but only on its denominator. Okay, so it will be the same matrix for 1/2, for 3/2, for 5/2, and so on, right? It only depends on the denominator of the corresponding rational number. All right. So now they found that we have a collection of interesting matrices in each bar, and they try to compare with some other examples of such matrices known in representation theory, and they made a pretty peculiar conjecture. So they found the following thing. So how would I describe it? Okay, imagine you have a Fock space. Fock space is a very natural representation of a quantum affine GLB algebra. So, and now you consider the action of GLB on a Fock space with B given by denominator of a rational number, right? Then there is a series of canonical bases for GLB, and on a Fock space, the canonical bases are usually described through some sort of involution. So if you consider the action of this algebra on a Fock space, it comes with an involution which is defined as follows. So on the coefficients which are function of h bar. By the way, now h bar is playing a role of, usually it's denoted by q, right? So now it's quantum group UH bar GLB hat. All right, so on the coefficients which are polynomials in h bar, it acts just by sending h bar to its inverse. Then the convolution actually preserves the vacuum, the highest weight vector in the Fock space, and it also preserves the action of lowering operators, right? So F is lowering operators. Fock space is like a Verma module, which is generated by Phi's from the vacuum. And then these three properties completely define involution of a Fock space. All right. And now, using that involution, we have two different bases. The so-called standard basis in a Fock space for GLB action. Something very well known. It is, if you're familiar with fermion formalism, it's actually a basis of infinite wage or fermionic basis in a Fock space. And then this involution sends this vector, sends this natural basis of a Fock space to something which I denote by lambda bar. And then you can ask, what is the transition matrix from lambda, from the standard basis of a Fock space, to so-called co-standard basis of a Fock space given by that involution? And so the interesting observation Zhenya and Andrey did is that this matrix, the transition from standard basis to co-standard basis for GLB, actually coincides with the transition matrix across the wall for the Hilbert scheme. And this conjecture is interesting just because it's quite, I would say, unusual. We don't expect an action of GLB hat on a K-series of Hilbert schemes, right? So where this action came from. This general construction of Maliko-Kunkov, which works for all quiver varieties, it predicts the action of this dim algebra or quantum toroidal, but it says nothing about the action of GLB hat. And so it's interesting where it came from. All right.
I ask a question.
Yeah, absolutely.
Don't you see a cyclic quiver of consisting of B vertices?
Oh, exactly.
The fixed point.
Yeah, that's gonna be later in my story. So we'll see, the cyclic quiver with B vertices. Exactly. Yes.
So if you consider the Barber shifts, constructive shifts on the cyclic quivers, then you can understand the standard basis and also canonical basis, right?
Exactly. Yeah. So those cyclic quivers will appear as fixed points of some cyclic groups of cyclic groups, and they will enter the story more or less exactly as you say.
Okay, thank you.
All right. So that was what was set, some of the conjectures of those papers, and now I would like to switch to elliptic stable envelopes and the way I see those conjectures from so-called three-dimensional mirror symmetry. So what's going to be in this talk? So in this talk, we're going to view these rational Schur functions, the basis of the Fock spaces, as limits of more general construction, So we'll talk about something like, you may think about it the following ways. There is elliptic generalization of these rational Schur functions. You can call them elliptic Schur functions. And all these guys will appear as different limits of those elliptic Schur functions. And the correct name for those elliptic Schur functions is elliptic stable envelope. It's something introduced by Akunkov and Aganagic and Akunkov. All right. And elliptic stable envelopes elliptic Schur functions have some nice additional symmetries, which you don't see in equivalent K-theory. And those symmetries usually called three-dimensional mirror symmetry, or in more mathematical literature, it's also called symplectic duality. Basically, I will have two related objects, Hilbert scheme X and the dual variety, symplectic dual variety, which is, in this particular case, it will be the same, it will be also a Hilbert scheme. So Hilbert scheme is self-dual with respect to 3D mirror symmetry. And then we'll see that, under this symmetry, elliptic stable envelope transform in a very natural way. Something which is usually lost in K-theory. In K-theory, we don't have this phenomenon. And then if you know this symmetry for elliptic stable envelopes, the conjectures of Gorski and Nigut will follow somehow as a consequence of this three-dimensional mirror symmetry. All right. Okay, so let me move on. Very briefly, so I don't want to go into details about elliptic gamology and stuff. Let me just very briefly say what is the difference between K-theory classes on the Hilbert scheme and elliptic gamology classes. At least on the level of computation, you can view this as the following story. So imagine, now let me introduce some notations, right? So I have a variety with an action of torus, like for example Hilbert scheme in this case, and let's assume that my set of fixed points is finite, and then let's say I fix some parameter q. It's going to be a new parameter, and I want to think about this parameter q as a parameter of elliptic curve. So I have an elliptic curve which is given by this ratio. All right. So what is the difference between K-theory classes and elliptic gamology classes? I can use a so-called localization in equivalent K-theory to think about K-theory classes as defined by their values at fixed points. All right. So basically, if you take a K-theory class, you can restrict it at different fixed points, and then these coefficients will be Laurent polynomials in all equivalent parameters, like in our story, T1 and T2. And the K-theory class is completely described by these restrictions, right? What is the difference in elliptic gamology? In elliptic gamology, we have more or less the same story, but now restrictions of elliptic gamology classes to fixed points, so these coefficients, now they are not Laurent polynomials, but they are sections of certain line bundles over elliptic curve given by rank of a torus T. So in our story for Hilbert schemes, that's going to be just E squared because my torus is two-dimensional. And now I'm going to think about parameters T1 and T2 as coordinates on elliptic curve, right? And there is a simple relation. So again, when I will give you, like in a minute, I'll give you some examples of elliptic gamology classes, and I'm always going to present them as some elliptic functions. And you should think about those elliptic functions as coefficients of some elliptic gamology class on the Hilbert scheme. And there is a simple relation between elliptic gamology and K-theory. So basically what you do, you take elliptic gamology scheme, that is a scheme over which all your sections, over which your classes are actually sections, right? And then if you degenerate your elliptic curve E into just C star by sending Q to 0, then the elliptic gamology degenerates to a scheme given by spectrum of K-theory, and in particular sections over that scheme degenerates to a sections of trivial bundle, to a trivial line bundle over that thing. So they basically give you a K-theory class, right? So there is some nice limiting procedure from which you can create K-theory classes from elliptic gamology classes. Important thing is that these stable envelopes, they will actually depend on one extra parameter, which I'm gonna call Kähler parameter. So basically, we usually have as many Kähler parameters as the rank of p car of X. And for the Hilbert scheme, p car is just one dimensional. And so my sections, elliptic sections, we actually will be actually sections over three-dimensional abelian variety, given by this product of elliptic curves with coordinates t1, t2. Those are my old equivalent parameters, plus one extra parameter, which I will denote z. And I call this parameter Kähler parameter. So why exactly we need this Kähler parameter in elliptic story? What is responsible for? So there is a general theorem that for every fixed point on a Hilbert scheme, there is a construction of Gamology and Akonkov. It's a construction provides you elliptic stable envelope. So again, that's going to be a section of certain line bundle of elliptic Gamology scheme. And so as a section, it will not trivially depends on all these three parameters, T1, T2, and T3. And more importantly, this section has the following property that in a limit to K theory, it degenerates to all these different rational Schur polynomials. What does it mean? So when you take a K theory limit, you send your parameter Q to 0. But as I mentioned already, you have this extra parameter Z, Kähler parameter. And what can you do? You can do the following. You can kill this parameter in the following way. You substitute Z is equal to Q to the power S. S, again, is some rational number. And then you send Q to 0. And then depending on S, you will have different limits. An interesting picture is that for, there's like many different degenerations. And for different values of S, you get exactly all those different rational bases of the Fock space of these rational Schur functions.
So Andrei, so on the level of elliptic functions, if you write it as a series, does it mean that the series truncates when you specify?
No, it's simpler than that. I'll show you why it happened in a minute. So basically, it's simpler than that. You have like you have a ratios of various theta functions, and you have some formula which describes. So no truncation of infinite power series is involved here. It's simpler than that. So basically, the picture here is the following. So you have, let's call it like elliptic Schur function, right? So it's a global class which depends on three variables, T1, T2, and T3, maybe 4 plus Q, elliptic parameter of elliptic curve. And then you may consider different limits as limiting Q to 0 of this elliptic class. And at the different points, you'll observe that it has different limits. So basically, the statement is the following. So the limit of that function is a locally constant function, which gonna change only across some walls. So in this picture is for Hilbert scheme of 3 points. And then the limit of this elliptic stable envelope will only jump at the points with corresponding to rational numbers with denominator not higher than 3, right? So that's exactly these points labeled here. And on each of this interval, you have the same limit, but once you cross the wall, your limit somehow jumps. And the transition matrix from the basis which you have before the wall and after the wall is exactly those functions, those things studied by Zhenya Gorsky and Andrey Negut. All right. So now we sort of can view all these bases as one. They sort of glue to one global object, and so it's better to study this object. Okay, here's a small example. So for instance, for n is equal to 2, you have 2 fixed points, and for example, you can take a stable envelope of a fixed point given by diagram 2. Right, so it's elliptic. this thing is elliptic Gamology class. And as I mentioned, you can ask what is the fixed point component of this class. So this fixed point component, they're given very explicitly by these formulas. So theta here denotes odd theta function of elliptic curve. It's given by this formula. And all coefficients are expressed through these theta functions with, which depends on T1 and T2 and Z. All right, so diagonal component restriction to the same fixed points does not depend on this new parameter Z at all, and only second component depends on the Z. And now just returning to the question asked by Peter, so where the this locally constant function came from, there is a very simple exercise with theta functions, just with this formula. If you know this formula, you can do the following exercise. If you take a rational, if you have a ratio of two theta functions, such that you have Z in numerator and denominator, you can substitute Z is equal to some to Q rational number, to Q to the power rational number, and then send Q to 0. And then what you get is actually monomial in X to the power, basically, so here his notation is a floor function for S. So it's an integral part of S. All right. So this floor function, its graph as a function of S is like this. Okay. So it's a function which jumps only at the integral point.
Andrey, sorry. The first fixed point restriction does not depend on T1, is it right?
Yes, it does.
Okay, thanks.
Mm-hmm. And then if you look at the second component, the only component which depends on Z, see here you see that it always depends on these ratios of theta functions, exactly as in this limit. And so to compute those limits, the only formula you need to know is this thing. So here depends on the ratio of theta functions depending on Z. And the second one depends on ratio of theta functions depends which depends on Z squared, right? And so the first coefficient is jumping at all integral points, exactly as in this picture. And this coefficient is actually jumping at all half integer points. And so if you consider the limits of these elliptic functions, they're gonna jump like at all points, at all rational numbers with denominator not bigger than 2. All right. So so this is very simple thing. You don't need to consider infinite power series. All right. Let me go and say what is the three-dimensional mirror symmetry. Well, let's consider.
Sorry. The question. Wait, question. Just to make sure, as on the previous slide. So this is like theta 1,1 or something.
Yeah, it's like theta 1,1. Yeah. So
yeah. So basically, yeah. Q to the S is like generalizing to rational. 1,1 means 1/2, and like you're basically taking 1 over something rational characteristics and taking the parameter to 0 is like the same thing in the language of theta function with characteristics, right?
Yeah. So what I describe is probably more familiar to you under the name of this Inozemtsev limit, right? So elliptic integrable system have many different limits to trigonometry. That's exactly what happened here. But now
you're shifting the argument by different taus, and the limits will be different. Yeah.
Right. Yeah. So it's a type of Inozemtsev limit for this dim algebra, if you wanna in this language. Okay.
That's interesting. So then the analog of the Inozemtsev parameter is what? It's like 1 over q. So q goes to 0. It's like the Inozemtsev limit.
And this is like dynamical parameter for in this case. Okay. So all right. Let me say what is three-dimensional mirror symmetry for this stable envelope. So the stable envelope has some sort of miraculous property you can consider the following matrix. Say you take stable envelope of a fixed point, lambda, and restricted to the fixed point mu, right? And so you have a matrix of restrictions, and those are, you should think about this matrix as a matrix with whose coefficients are elliptic functions of a, h bar, and z, right? So examples like these two restrictions, for instance, right? It always will be something like this. You know actually combinatorial formulas for those. And then we have a miraculous property of this matrix, which says you the following. If you take this matrix and change a and z, so you take, you exchange equivalent parameter a, I recall that a was ratio of T1 and T2, and z is this extra parameter, scalar parameter or dynamical parameter, which appear only in elliptic Gamology. Then it's actually, then this matrix is actually symmetric with respect to this change. And that is what we call three-dimensional mirror symmetry for elliptic stable envelopes. So elliptic stable envelopes have this amazing property, has this amazing symmetry between equivalent parameters and scalar parameters. And this property, of course, is absent in K-theory, because I mentioned when you consider K-theory limit, you actually kill Z. Z will not survive in K-theory limit. And so on the level of equivalent K-theory classes or like trigonometric classes, you cannot observe it. But in elliptic situation, that's actually very explicit.
Andrey, very stupid question. What is the restriction? How do you restrict?
How to restrict? So you consider stable envelope. That's a class, elliptic Gamology class, and you restrict it to the fixed point. So you're asking what is restriction, like how it mechanically works? Or,
but you constructed it already on fixed points now.
Not really. So you can write some sort of explicit formulas for these classes, expressing them in so-called elliptic churn roots. And then restriction to the fixed points corresponds to some substitution of churn roots. But I'm not sure it explains things, but that's how it works. Again, it's not super important. Just think about this matrix as a matrix with this type of entries, right? And then you know somehow that it has some amazing property.
And you actually wrote that it's like invert in the inverse in the parentheses.
You need to do something with that matrix, like invert it, or well, stable envelopes depends on a bunch of parameters which I'm not writing here, like a choice of attracting directions or like a choice of some chambers in your torus. And then basically you need to invert the chamber, which on the level of these matrices, it works like inverting the matrix itself. Yeah, so you need to do something.
So it looks like a modular transformation of some sort, or this is just superficially, it looks like inverting like what happens with like period matrix when you invert the tau, the period matrix of the four elliptic systems, the corresponding period matrix will like the transformation will look like this, like something like this. The matrix will be inverted too.
But elliptic parameter is Q, right? It's not H bar.
It's not the same. I'm not saying that it's the same, but like the matrix transformation looks the same. When I'm just saying it's like something like a modular transformation. Whenever you have like the inversion, it's like modular transformation or something. But I mean, it looks like, I'm not saying it means anything. It just looks like.
Well, maybe it's related. Here I cannot comment because I don't know. Like
yeah, I'm just saying it looks like it.
Okay. Maybe in the end everything will, be the same science. Like all sciences should go to the same common point at the end. So we have this property of that matrix, and I will refer to that property as three-dimensional mirror symmetry. All right, and so now I wanna do something which look as follows. So I want to slightly modify my k-theoretic limit so that the scalar parameters survive. I don't want to kill them anymore, but I want to do something slightly more general. So now I want to consider, and that's actually what we do in our paper with Yasha Kononov. We wrote a couple of papers about this procedure, which is actually very simple. So in a Aganaj-Kakunkov limit of elliptic stable envelope to K theory, what you do, you substitute Z to be q to the rational power S, then send q to 0. Now what I want to do, I want to do the following. I want to keep Z. So I'm shifting Z by q to the power S, not substituting, by shifting. And then I send q to 0. So why it's interesting? Well, because now you basically, again, you need to know only what happened with this ratio of elliptic functions. Now with Z shifted by q to the power S. And in that limit, when S is not integral, you arrive exactly at the same limit, which actually does not depend on Z as before. And so all these k-theoretic limits of Aganaj-Kakunkov for non-integral slopes will stay the same. So I'm not going to change anything. But a new phenomena appear at integral slopes, at integral S. So at integral S, the limit is slightly more complicated. So there's an additional factor which depends on Z, survive. And so at those slopes, which exactly corresponds to the walls in my picture, I have some sort of new k-theoretic limits which corresponds, which in addition will depend on Z. So on picture, it looks as follows. So you have again this elliptic Gamology class, elliptic Schur functions. Now, if you consider the limits of these Schur functions in between the walls, you get exactly Aganaj-Kakunkov, it's not Aganaj, it's Malik-Kakunkov k-theoretic stable envelopes. But now you can do slightly better than that. You can consider the limit into the wall, right? So exactly to the wall. And what you see here is some new k-theoretic classes, which additionally depend on some extra parameter Z. So far we don't know what this extra parameter, but three-dimensional mirror symmetry suggests that this Z is an equivalent parameter on a dual Hilbert scheme. All right. So I basically maybe need like 5 more minutes to finish it. So let's consider this matrix of restrictions. As I said, T was a matrix which was constructed as follows. You take stable envelope of some point lambda restricted to some point mu. And so you have a matrix labeled by lambda and mu. Now you can do the following. Consider some wall in my picture, right? So it's a rational number corresponding to the wall. As I mentioned, you now using this enhanced limit, consider the limit to the wall. And here you get some matrix, again, some matrix with trigonometric, like rational functions in all equivalent parameter A and H bar, but in addition on this parameter Z, which survive. And you can also do the limit immediately before the wall and to immediately after the wall. And then there, before and after the wall, you have matrices which do not depend on Z. So those are the matrices of k-theoretic stable envelopes with slopes S minus epsilon and S plus epsilon. Right? And the k factorization, the k observation about this strange thing in the middle is that this matrix actually factorizes. So the k factorization, k observation is the following. If you take this matrix, which depends on all these 3 parameters, and divide it from the right to any of these matrices immediately before or immediately after the wall, does not really matter, then the result is actually a matrix which only depends on Z and H bar. Right? So dependence on A completely factor out through this procedure. And that is actually very, I would say, maybe the most important point of this talk, because it's a very non-trivial thing. So imagine you have a matrix which whose matrix coefficients are rational functions in some variables. It's almost never happened that this matrix is going to factorize so that product of two matrices which depends only on one half of parameters and the second depends on the other half of parameters. And here is really some miracle happen. So there is this factorization. And so the matrix A is a matrix of k-theoretic stable envelopes with slopes before and after the wall. And now the question, what is this matrix Z? All right, and then I return to the question asked by Hiraku. So, so here's the theorem. And of course, we're going to use, we use this three-dimensional mirror symmetry of elliptic stable envelope matrix to derive it, but here's the theorem. So again, matrix of the limit to the wall factorizes to the product of matrices which depends only on Z and matrices which depends only on A. Matrices A are matrices of k-theoretic stable envelope of X with the corresponding slopes S plus epsilon, S minus epsilon. The matrix Z is a matrix of k-theoretic stable envelope, again, of some sub-variety in a dual Hilbert scheme with some small slopes plus minus epsilon. And so who are these sub-varieties? The sub-varieties in the dual Hilbert scheme appear as fixed points of some finite groups, of some finite group, which is just a group of roots of a unit. So it's basically ZB. And B is a denominator of a wall to which I consider the limit. And so it basically acts on a dual Hilbert scheme by scaling the scalar parameters like this. And again, I recall that on a dual Hilbert scheme, Z corresponds to some equivariant parameter. And so, so it means that Z is a coordinate on some torus, which is acting on a dual Hilbert scheme. And so it appears that all the connected components of this sub-variety S are exactly the Nakajima-Quiver varieties, cyclic Nakajima-Quiver varieties of length B. So here's how it looks in this picture. So if you consider the Hilbert scheme of points with this action of finite groups, you have this loop L, and then these roots of unity act on a loop by just scaling the loop with a root of unit. And you want to ask what is the set of fixed points with respect to that action? Well, here's the answer. So YS, its fixed point components are labeled by Nakajima-Quiver varieties, which are cyclic Quiver varieties with different ends in this picture. And now, of course, you know that K-theory, again, the K-theory of this cyclic Quiver varieties are nothing just but fork modules of UH bar GLB. Again, B is a denominator of my rational number. And it sort of explains where all the story with GLB, with GLB matrices in Gorsky-Nigut picture come from. Now the proof of Gorsky-Nigut conjecture is like super elementary if you know this thing and if you know factorization, if you know this type of factorization. So how the proof goes? The proof goes as follows. So consider a wall located at a point A divided by B. You consider the limit to that wall. And as I mentioned, the limit to that wall has factorization. So you can factorize variables A using the matrix of k-theoretic stable envelope right after the wall. Or you can factorize the same matrix using the matrix of k-theoretic stable envelope right before A. So basically you have two different factorization of the limit to the wall. And now you just send all matrices which depends on A on one side of this equation here, and all matrices which depends on Z on the other side of this equation. I guess he's going to be minus one side, so something missing here. So it's going to be matrix A to the power minus one. Oops. All right, so basically what you have here, you have a matrix of transition between k-theoretic stable envelopes before and after the warp. Exactly the matrix which is studied by Gorski-Good. So it's a transition matrix between one basis to another basis. And on the other side of this equation, you have stable envelope with some small positive slope on a cyclic Fourier variety and stable envelope on the same cyclic Fourier variety with small negative slope. And that is exactly the transition matrix between standard and co-standard bases of the Fock space, just because it's known very well that the standard and co-standard basis corresponds to a basis of stable envelopes with small positive or negative slopes. So it's like become completely elementary. And okay, so here's the proof of that conjecture. And just a final remark that today I was talking about Hilbert scheme of points, but of course this is just one of many examples you can study stable envelopes in. For instance, you can do varieties like T star G mod B, and the elliptic stable envelopes exist and well defined in those cases. And three-dimensional mirror symmetry exchange now X with X dual, which is in this case T star of G mod B Langlands dual associated with so it's flag varieties associated with Langlands dual groups. And yeah, and basically for it would be very interesting to study this story, for example, for ball varieties. So ball varieties are very interesting in a sense because they're closed with respect to the mirror symmetry, three-dimensional mirror symmetry. If you take a mirror of a ball variety, you get a ball variety again. So it would be something, at least on a level of combinatorics, it would be very interesting to compute elliptic stable envelopes for those cases and study their symmetries. And lastly, the thing which I didn't discuss today, but this story has a lot of very interesting applications to quantum difference equations associated with X and X dual. And but maybe that would be the story for the next talk. All right, that's about it. Thank you for attention.
Thank you very much, Andrey. Yeah, for a very detailed talk. Okay, so we don't have much time for questions. Maybe there is a quick question we can accommodate before the next one. Yeah, just feel free to ask a question if you have any.
I can basically just comment quickly on the same question. But if anyone else has a question, I can step aside because I already asked it. So, anyone else?
I guess Hirako
Okay.
wants to ask something.
Just one question. Can I?
Yeah, go ahead.
What kind of KZ? I don't know. It's a KZ-like equation you have from this kind of setting. Can you write some explicit examples, simplest possible?
You're asking what is the KZ for?
Yeah. So no, my question is too naive, probably. So can I guess?
No, that's a perfect question.
Can I expect some kind of KZ equation? Which
let me ask you, are you asking about Hilbert's scheme or like in general?
No, in general, probably.
Well, in general, there is a very large story about q-difference equations, and the story is the following. So if you consider quiver varieties, you can ask, you can study, so in a natural way, q-difference equations in equivalent parameters associated with quiver varieties. And so in particular, as an example of those equations, you discover all Knižnik-Zamolodchikov equations, but even more interestingly, you will discover some interesting generalizations of Knižnik-Zamolodchikov equations. And on the other side, you will have difference equations in Keller parameters, and those are difference equations you know, those are dynamical difference equations in representation theory. And those dynamical and difference equations and Knižnik's homological equations, they are exchanged by this three-dimensional mirror symmetry.
Okay, thank you. So I think we need to go to the next talk. Yes, it's already 6:10. So I think we can continue the discussion over the email, or yeah. So yeah. So there will be other days in the workshop. So yeah. Okay. So thank you very much, Andrey. Okay. So now, Junichi, you can share the screen now.
Do you see something?
Yeah, we see the PDF. Yes.
And do you see?
We can see it. We can see a cursor. Yeah. Okay. We can start whenever you're ready. Yes. Okay. So the next talk is by Junichi Shiraishi from Tokyo, and he'll be talking about branching formula for q-Toda function of type B.
Okay, thank you very much, Peter, for the invitation. No, today I'm not elliptic, and I'm just trigonometric. Nothing.
That's okay. That's okay.
No, no. So far it is just trigonometric, but and again it is not clear how we can relate such thing with cohomology, K-theory, geometry, whatever. Anyway, so my story is about some explicit formula for the q-Toda system of type B. Now, why B? So there are B, C, D, but C, D, I don't know the result. The structure is much complicated compared to this B case. And okay, so what I want, I wanted to show you some explicit formula which is working for BN q-Toda, which was conjectured by Ayumu Hoshino and me some time ago. And then after that, I was trying to find some easy proof for that kind of formula. And then fortunately, so there is very elementary proof for this statement, which I'm going to show you. So nothing is complicated. It is just straightforward calculation. But at least we see some nice structure. So this is the thing which I want to explain today. So anyway, so it has been introduced in the previous talk, the things like McDonald polynomials, but let me try to do it again shortly, starting from AN case. Why I need McDonald? Because I consider McDonald as central object of my research, and I sometimes take Toda limit. Toda limit is what? Toda, we have Q and T parameters for McDonald, and if I take T0 limit, by some reason we have Q Toda equation and q-Toda eigenfunctions. So let me try to explain what is this. So we have coordinates x1, x2 to xn, and we have some kind of spectral parameter which specify the Young diagram for the McDonald polynomial. It is discrete parameter, but sometimes it's better to consider some analytic continuation of this lambda parameter. And I call it like S1 through Sn. So in total, we have 2n coordinates, x1, xn, s1, sn, yes? And by some reason, we have this staircase partition, so which is introduced to control the shifting of the spectral parameter, which is important before taking the T0 limit. No, so it is clear. I will explain. But the very naive limit, like T0 only, without any shift in the variable, will not give us the Toda equation. So anyway, so this is
just coincidentally, it's the same limit as was discussed in the previous talk, right? So we already seen it's a q to 0 limit in Andrey's notation.
Yeah. But so you see, this is a McDonald operator. But if you just take T0 limit, you just kill this, and you still have the denominator. So that is not good for my purpose. So I have to first scale x here somehow, like here, and then take the limit. So that means if I'm no, so what is u? I forgot. But no, like here. So I shift x to the t to minus delta x, yes. So then take t0 limit. So after that, we have very simple looking difference operator, which has a just next neighboring kind of coupling, as is in the original Toda lattice. I mean, in the McDonald setting, everything talk with each other. They can be very fun, but just adjacent things can appear in the potential. That is the Toda. Yes. So because we can take such limit in the operator, so we can take the similar limit in the eigenfunction. Then that will give us the eigenfunction for the AN Toda difference operator. So just let me briefly recall what kind of combinatorial formula we have for the McDonald polynomial of type A. But it's better to do it here, not with polynomials, but with some formal power series, which is extended in one direction. One direction means it is actually the support of such function is in a dominant cone of an-1 algebra spanned by such monomials. No, so just to be clear, so what is here? So we have x2 over x1 here, and x3 over x1 here, x3 over x2 here, and so on. We sum power, yes? Then we have such big summation, where such theta ij from 0 to infinity. So that is giving us some formal power series, which I call kind of asymptotically free eigenfunction to the McDonald operator. And no, so the problem is how we can find the coefficient here. no, before. So why it can be a problem? So the monomials which I wrote here, they are not free. So they are over complete. It is clear that so x3 over x1 can be obtained by multiplying these two. So they are very much redundant. So that means the expression here we have for Cn can be very much different. So there is up to such quotient of the over complete things. So the freedom for Cn is huge, and usually it is not easy. Usually, I mean, I do it for an minus 1, and by some reason it is possible. But once we go to the other cases, like Bn, Cn, Dn, we have, by the way, so we have some more parameters, Q, T, T1, T2 for B, C, and for D, we have Q and T only, but so we have McDonald operator, and for B, C, D, and we can try to diagonalize it, assuming the function has such expansion associated with the dominant cone of the algebra. It is good, but so the coefficient is not easy to find because of the problem which I explained. But as I said, as I was saying, is for an, and so by some reason we can achieve such kind of factorized expression for the coefficient here. So let me just remind you what is the reason for this kind of combinatorial expression. So one reason, maybe from the combinatorial point of view, we have the kernel function business associated with the McDonald difference operators, and which is giving us some kind of reproducing kernel integration transformation, which can be iteratively used to construct complicated, more and more complicated wave functions by some integral way. By the way, so this integral can be just Cauchy integral or by Jackson integral. If I do it by Jackson integral way, I have this kind of formula. So this is probably best explained in the paper by Masatoshi Nomi and me some time ago. So if you're really interested in such detail, you just try to see. The other reasoning for the factorization formula for this type is coming from a geometry. So that is Roman space. And so there is some geometric investigation of the structure of such variety. And long ago, it was found by Braverman, maybe with other people. So the structure of the tangent to space to this space. And if you just look at the structure, so you just know what should be the denominators here.
That's right. So there is that interpretation, and there's also another one using vertex function of the cotangent bundle to the complete flag variety. So essentially it's the same thing, but the derivation is different. So like this f an minus 1 is the K-theory vertex function.
Okay. Yeah. Vertex. Yeah. I was
vertex with E. Yeah. Physicists call it vortex function, which is essentially the same thing.
No, I'm not familiar with this vortex function business, but somebody has explained me something, and I vaguely understand. But so there are many ways. Yes, thank you.
A way to show that Breverman et al. Calculation is equivalent to that one. Yeah,
yes, and what's the motivation of my talk today? So I'm just proposing some kind of formula which works by combinatorial way, but I know nothing about the interpretation. So if you are very kind to find something interesting behind such combinatorial formula, I'm very happy. Okay, so I have nothing to explain you, but some combinatorics. No, so again, so this A-type formula is very nice. You have many ways to understand, but formulas which is behind it, beyond this, for example, type B, C, D. Now, by the way, so I know nothing about CD in general. Of course, I know something for small n, small ranks, but anyway, so the example which I'm showing you today, I mean, Bn, n in general, for Toda. Toda means T0. It is something I could find which works for general setting, like Bn and general. So I vaguely guess that there should be something behind it, but nothing is clear. No, yeah. So as I was saying, and Peter was helping me all the time. So we just take T0 limit. Anyway, where is T here? All the T parameters are sitting in the numerators. So the T0 limit here, very simple. And almost all disappears in the numerator. And something remaining in the denominator gives us the Toda coefficient, like here. No, it is product of some factorial sitting in the denominators. So then the claim is, if I substitute this kind of thing here, and I call it f of an minus 1 to the, for example. So then we have this eigenvalue equation satisfied. So then I do the similar for B. So maybe it is clear already to you, but let me anyway try to introduce the T0 limit from the operator. I mean McDonald operator. McDonald operator for type B. So by the way, so McDonald himself probably did not write this kind of operator for B, or he did, I forgot. No, he constructed the operators associated with some representation theoretical data. So, but there is another way coming from Conway operator. Conway operator, it is kind of operator of this form, having A, B, C, D parameters somewhere here. Here, together with some zeroth order operator, I mean some multiplication operator by some rational function. But if I write the special case of co-wind operator for ABCD is T minus 1 Q1 half minus Q1 half, I have this operator. And plus, in this particular case, it is just constant. So it is known that this is just commuting with McDonald's Bn operator. So diagonalization of this gives us McDonald polynomial of type Bn. Yes. As I was explaining for An case, I do the similar T0. Sorry, I didn't explain for A, but so by some reason it is reasonable to making such kind of gauge transformation by x to the lambda to have some s like parameters sitting somewhere inside the operator itself. So it is it simplifies many things. And here I do the same trick as always. And after that, what I do. So then I try to make some shift. It is written here, but let me write it somewhere. So I have to make some very particularly carefully chosen shift in x. Then take t to 0 limit. So then, I mean, so I need to put -1 here. -2 doesn't work. -3, 1 doesn't work. Only -1 works for killing all the denominators here, 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 and giving us something non-trivial operators as a limit. So this is a limit, and this is the thing which I start from today, for today. Anyway, let me try to have a look at this operator. Now, I need to understand the structure of this operator a little bit. So first, what we have some operator which is inside this blue. So I mean, if I remove this 1 over xn thing, so we have an -1 Toda. And if I look at the rest here, so it is again the an -1 looking, but so parameters are kind of replaced to kind of inverse. I mean, S1 is going to 1 over S1 as usual in the representation theory of Bn algebra.
Yes, that should suggest that the Dynkin diagram of
automorphism. But so here you see, so there is something which is not inside the A business. So that is Sn, maybe minus Sn over Xn times Q TQXN. Yes. So anyway, so all the time things are like this, not only for B, but also for D, C. So let me stick to Bn case. I'm just trying to understand who is this guy. Very simple operator, which is outside of this AN looking like operators, which makes everything into Bn business. Actually, so the action of such operator to somewhere has to be clarified to understand the eigen functions. Yes. Okay. So let me move on. So now it's time to probably hurry up.
It's okay.
So,
There are 25 minutes. Yeah.
Okay. So where I do the diagonalization first, let me specify. Otherwise, it's strange. So we have an formal power series whose support is given by the positive cone of root lattice corresponding to Bn. So that means we have this probably negative epsilon2 minus epsilon1 looking like simple root epsilon3 minus 1, 2 up to epsilon n minus epsilon n minus 1, and here minus epsilon n. So this corresponds to the short simple root for Bn. So if I include everything and span the positive cone, put unknown coefficient in front. So this is my function. And ask when we have this eigenfunction with prescribed eigenvalue. So if you do it very naively, it is just a mess and you don't see anything. But if I decide to make some kind of branching formula structure behind it, so that is the idea. So if I expand this Bn thing in terms of An Toda, multiplied by such short root contributions with some coefficient. So actually, so this is giving us some kind of functions which is sitting inside our function space. And then suppose it is so, and just plug this kind of ansatz here. So then I find immediately that so this branching coefficient E or Bn over An minus 1 with theta 1 up to theta n totally factorized. So I did it by mathematical calculation, starting from B1, B2, B3, not B1, maybe B1, yes. Maybe I did it for B4 or B5, and no exception of such factorization found. So then it is rather easy to guess the general structure. So this is written here. So this has been reported in some journal with Ayumu Hoshino some years ago. And today I just explained how it can be proved. No, so actually the proof is very simple. But anyway, let me try. So at least a few words about the structure. No, structure is just almost everything downstairs. I mean, some q factorials here, but we have some unclear factor upstairs here. So we cannot avoid this if we try to follow this way. So anyway, my question to you for today is how we can understand this kind of this kind of structure. So if you can tell me how we reproduce such a combinatorial formula from some other technique, so that will be very good, very interesting to me. So anyway, so let me just show you some examples to be very sure. So if I do it for B2 over A1, it is this. And if I do it B3 over A2, this, yes. So as I told you, so we have so these strange factors in the numerators, which I don't. No. So there are several ideas which may explain this kind of things, but I do not have good enough understanding, or I don't have simply time today. So now I show you two key formulas which is needed for the proof of the eigenvalue equation corresponding to the B. So first one, it is about the behavior of the AN function. What kind of behavior I need to know. So here xn is q shifted. You remember that we have Sn over Xn like junk term appearing in the Bn operator. And at least I need to understand the behavior of this operator on this An part. Because I do it by branching way, I first expand everything in terms of A and try to know the coefficients. And experimentally it works. And so now I'm going to have a proof. So so this is a remark that I only need to shift to Xn. I do not touch the others. So then what can be expected? So I have to find some expression which is sitting inside the expression which I have started. That means I do not touch X at all, but I may shift S parameters because my function is sum over such AN todas with different Q shifts because of such summation over theta. So if I understand how to modify such expression as a summation of such thing with some rather controllable. No, in this case, very simple expression, rational expression, so it is enough. So we call it some kind of contiguity relations because we know some examples for Gauss hypergeometric, which we know. So we have many contiguity relations. Contiguity means suppose this S side is kind of accessory parameters like phi to 1, A, B, C. So A, B, C like thing for me is this S parameters. I'm changing S and asking what kind of relations we have. So because of this reason, I call this contiguity. So here I just have some notation, but it is clear So it is sum over k from 1 to n, and shift in S is just one particular place.
A question. So does the contiguity relation and the branching formula, so do they exist also for McDonald's, or for the eigenfunctions of McDonald operators?
No,
or
so
not?
That's very good question. So as I was saying, difference operator for Toda, so that is very kind of nice. Only the next adjacent things can talk with each other. So that by that reason, the difference from Bn and An, that is very simple. Just Qxn.
I see, because there is only those particles which are next to each
so
other.
if I do it for McDonald's, I have to take care of everything. Everything means everything with the denominators.
I see, I understand. Yeah, thank you.
That is mess. No, I was trying to do it, but it is rather uncontrollable for the moment. So, but maybe we can be better, clever in some way. I don't know. Thank you for asking. So at least this kind of thing works nicely for Toda limit. And it is immediately clearly seen that so this identity, which is not so clear as is here, is just equivalent to this rational function identity. So once you prove this automatically. Okay. So I need one more. One more on this. So if I hit by the Bn Toda operator, this ansatz for Bn, it is sum over n minus 1 with some coefficient which I call EBA. So I could express this as very nice form as which allows me to make some recombination of the summation. I mean by the contiguity relation. So then after that I need to play with this coefficient E, and because I know the conjecture, then I suppose that it is true. So this E should satisfy rather nice recursion relation. No, so because I know the goal and I have a good control of everything, and I could. No, it is easy to find this kind of identity should hold. Yes, and then you just make ratio of this and simplify things. So it is clear that this kind of identity is just identical to this kind of, again, rational function identity. No, by the way, it looks very nice. So no roots here. So there may be some good reason to be to have such things. So then let me just give you a very brief sketch of the proof, how it goes. So I want to show that this f of b is an expansion of f of a times some coefficient with such roots multiplied. And as I was saying so many times, so we have this junk which is slightly different from A part. A part, I mean, so the first A part and then the next A part. And I really need to study the effect of this chunk. Yes. So I call this right-hand side just like this for short. So then Toda operator acting on this right-hand side is just, no, so here I just write it as it is. So this young plus first A-Toda, second A-Toda, which is kind of dual to the original A. No, so they commute. So because they commute, so they are acting by number, because I have already diagonalized such eigenvalue, such eigenvalue. And then I need to explain what's gonna happen here. Yes. So now I use the contiguity. Contiguity gives us this with F with some extra shift. Yes. So then now I reshuffle everything and use this part, that part, this part. So that is the recursion which I explained for this, and after simplification, we just have this eigenvalue equation proved. Yes, that's all, and then I just can stop here, but let me show you some fantasy kind of questions. The many things are still open. I mean, so C and D and q-Toda are still open. I do not know in general. So the structure is very, very complicated compared with this B by some unknown reason. So I do not know BCD McDonald eigenfunctions. It's complicated, and I do not know, of course, the Conwider case. Conwider polynomials with ABCD QT completely generic. I don't know. So if it is for A, we have some kind of geometry, or affine A can be. Now, if we do it for affine A, we have some elliptic integrable system associated to this problem. But so what can be the counterpart of this story for BCD? So that means what kind of treatment we may find for Drinfeld Zastava spaces for BCD? That this no idea. But anyway, suppose it is possible. So something like that. So anyway, we have some combinatorial expression for B and Toda at least. And do we expect something like Nekrasov partition function business behind it? I mean, AGT or something. Or some quantum toroidal algebra, dim algebra.
Yeah, so that would be the gauge theory with orthogonal with the SPN, like with a BN type with BN type group, right? So it's I'm not sure if the calculation was done in physics literature, but at least that's part.
Yeah, I was always asking to such people who is doing such BCD gauge theory, and I was trying to compare such thing with this kind of McDonald or Toda, but for the moment I have not been able to identify these two. So that means something is still unclear to me. No, so there are many. By the way, so we have a kind of BC W algebras that is coming from Frank Resetechin, or recently by group like Feigin, Mufin. Jimbo, and collaborators. But so no one can extract some McDonald's story from such kind of double algebra stuff. No, it is clear why it is impossible in a naive way. So it is again some puzzle.
Well, the AGT has the AD classification, like the classification of the 2,0 theories. They can only exist for AD. So you could get the B by orbifolding, but you cannot get BC by orbifolding.
Okay, 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 but no. So I want to have some explanation like this. Maybe it is not like gauge theory, but something else. Okay, that's also fine. So this morning I was trying to think a bit about the Dell version of BCD, Toda or McDonald. Maybe it is possible, probably not so complicated. But again, this is kind of fantasy for the moment. If you understand more, I'm very much interested. Okay, thank you very much for your attention. I stop here.
Thank you. Thank you very much, Junichi. Are there any questions?
So maybe I can ask.
Sure.
So it was about Toda limit, but how about the limit when T exists? Is it something known for Bn with T included? That one question, and maybe the second question is, like in an case, I have some sort of symmetry between X and S, right? Which exchange variables X and S. So what would we expect in Bn case?
No, in BC case, it is known that this kind of symmetry is just given by Lagrange dual. So you need to exchange the algebra for S side by Lagrange dual.
Right, but that is probably when T still turned on, right? So
no,
is it
T, with T, of course. T. No, and with ABCD. You can have ABCD QT. And you have a dual to these ABCD parameters that usually is written like alpha, beta, gamma, delta. So then it is explaining the Lagrange dual in this Bn, Cn, Dn McDonald setting.
right? But as far as I understand, you somehow always try to work with the Toda limit. Is there the reason for that?
No, so no, the main reason is a psychological one, but also technical. So Toda is simple. But McDonald formula, which I expect for ABCD, I mean some combinatorial looking like formula. What I know that it should be very, very complicated. That cannot easily be guessed from. No, I know, for example, Bn Toda. If I turn on T, that will give me McDonald. Bn. That is correct, but so such thing for small rank like B2 is durable. So I can easily see what should be the extension. I can do it for B3, but starting from B4, I know it is totally suddenly becoming much more complicated.
But maybe at least using computer, it can be checked, like everything works.
No, it is not easy to explain. But so my imagination about such asymptotically free expression no, does not work.
I see.
Some really non-trivial algebraic structures has to be there, which explains everything like PLE rules and everything in detail. So that should be not easy. Maybe for other people like you, so it is easy probably.
And because Andrey, look at
No,
on the surface, it's like some wall crossing formula, right? So you would change the slopes and then take a sum. It smells like it. I mean, the branching formula itself, right? So for
branching formula and slope probably a bit different. For me, slope comes when we do the elliptic things. No, maybe not. So I didn't. I forgot, but. So for AN case, if we do the affine, so we have some non-stationary version of the Rasnas elliptic system, which is not clear till now. And we have some kind of yet unknown system that is kind of non-stationary nature. Suppose it is so, and what kind of things we expect if we do the elliptic Fandi and Hikami Komori system? No. So I mean, so if I do that things with affine counterpart carefully, so it leads us to some non-stationary version of Fandi and Hikami Komori. So this is some stupid question, maybe.
Well, I guess what you're asking, maybe not about general situation, but at least for q varieties, there is an explicit way to write down those asymptotic solutions, like very simple way which give you combinatorics for free.
Yeah.
And for example, if you take a q which is affine, for example, like cyclic q variety, for instance, you'll have some some sort of vertex functions which are basically asymptotic solutions of some Toda like of some McDonald-Rudge like systems, as far as I understand it. But the problem with your case is that those T star G mod B for G not of A type, those are not q varieties, and well, I have the same difficulty of how to write those asymptotic solutions. Well, in BC case.
No, concerning the first part of your question. So I know such clever way of writing such kind of variety, and it is good. And I mean, it is enough to describe the Toda. So it may have singularities, but it doesn't matter so much probably. And because of this reason, we have some kind of integral representation for the probably Bn Toda. I mean QBn Toda, which I learned from Lyubnikov, Finkelberg long ago. And I was trying to compare such integral with this kind of much direct combinatorial formulas, and it works. But taking the integral is really hard, and making such calculation for me is almost maybe too much. So that means I still have not good enough understanding about the connection with Krieger story. And if we really need to do it for McDonald, it's better to have our variety smooth. And then I do not know what to do. The second part I forgot. Yeah, second part is maybe this kind of treatment of the things from geometry. Yes.
You're just saying that you're saying that the Macdonald operators and Macdonald asymptotic functions are not known in D case. Is that right? Is that what you said?
You mean D?
Dn, yes. Or are they known? Because you said in the end, right? So last.
So first, we have many formulas which works for the creation or writing Macdonald polynomials explicitly, like yeah, so I forgot the name, but so we have many ways. The recent one is some young Japanese. I forgot his name, but we have many ways. But at least for me, it is all the time kind of puzzle to have some understanding from the point of view of asymptotically free like expression. So that should be some kind of combinatorics, but
there's another way to understand the B series from D series by sort of orbifolding over the automorphism of the Dynkin diagram, right? So like you get the
I understand you, but
if B part is known, but I'm not sure if anybody did any. Like, I know some physics papers.
What I can do, I can do that explicit diagonalization by Mathematica first.
Okay, I see.
So that always tells me that everything starts really complicated. If I speak about the D or C, B is exceptionally simple.
That's surprising because I would say normally simplest series are easier, right? But in some sense, but maybe not. Yeah, anyway. Okay, any other questions? Okay, I don't see any. Great, so thank you very much, Junichi, and thank you, and Andrey. It was a great day. So we'll meet again tomorrow morning at 9 a.m. US Pacific, and whichever time you'll have at your place. Okay, guys, bye. Have a good night.
Thank you.
Bye.